Speaker of this afternoon. We go to the second speaker of this afternoon's session, who is Peter Markowich. Peter is a distinguished professor here at KAUST in the AMCS program. Peter is very well known for a variety of things, including being a fellow of the American Mathematical Society and an ordinary member of the European Academy of Science and Arts, and he's held positions at Cambridge, University of Vienna, TU Berlin, and Purdue. And he's going to be speaking on a measure-based approach to Mesoscopic modeling, optimal transportation networks. Please take it away, Peter, and thank you for coming.
Well, thank you very much, AJ. Well, first of all, thanks to the organizers, my friend Raul and my friend AJ, in particular to AJ, for having come over from all the way from China just for sharing my talk and talking watches with me. So, very good move on your side. Optimal transportation networks in biology. They are simply the most important and ubiquitous structures that nature can deliver. They, as I will show you in a moment, they occur practically everywhere in nature, around us, and even in our bodies. And they have had a lot of scrutiny from biologists in the recent decades, actually. And by now, I would say biologists have more or less agreed that transportation networks are emerging phenomena, whose evolution, development, and functioning is basically driven by the demand of the tissue within which you find the network. Okay, so there is, in general, there is no central control or central organ or something that steers the development of the networks. It is an emerging phenomenon driven by the demand of the tissue surrounding it. That's basically the main outcome of biology on it. And this is also the basis for the mathematical modeling that I will show you. Yeah, actually, I should say that this is a project that we have started quite a while ago, jointly with Jan Haskowitz, who is here, and Benoit Pertam from Paris. I think we started probably in 2012 or something to work on that stuff, based on work by the late David Tsai and his research group. In the meantime, many other people have joined in the team, and this latest part of the research is actually joined with Simone Portaro. I can get this to work. No. Simone Portaro, my PhD student here at KAUST, then Jan Haskowitz again, and for the numerical part, Clarissa Stuto and Giovanni Russo. And yeah. Okay, so let me show you some examples, some almost trivial examples of biological transportation networks. So what you see here on the left-hand side is a network of arteries. Arteries within which, of course, blood is being transported. In the middle, what you see is an image of a network of neurons, neuron cells. Well, they're basically those cells that make our brain work in the way it works. Okay, so they're the most important component of the brain and of the brain. And basically, what happens here is, this is funny. Okay, I'll give up on this and do it locally. And what is being transported in a neuron network is electricity, but the transportation of electricity works through the transportation of ions. So basically, you have to think that ions are pushed from one neuron cell to the other through those little flagella that you see connecting the neuron cells. Well, on the left-hand side, as you see the most common biological transportation network, that is leaf venation, right? You go to your garden, you pick up a leaf from any plant, and you will essentially see a picture like that. And what is transported here is, of course, nutritious fluid for the plant and the chemical which itself makes the network and the plant grow. Okay, so here you have three very distinct, very different examples of biological transportation networks, but they have a lot in common. What they have in common, what they share, is really a very complex geometry and a very complex topology. And this is what I sort of want to explain here in this talk. Okay, so first of all, let me begin by something pretty classical. That is a microscopic model of a transportation network. So basically what we have here is we assume the network is given by a graph. What's a graph? A graph is a set of vertices and a set of edges. Okay, so what I have here is an abstract graph, so there is no geometry involved, except that I'm assigning length tails to the edges. So Lij will be the length of the net of the edge that connects the vertex I to the vertex j. Okay, and what we are going to do is we are going to describe important physical quantities on that graph. And those quantities in particular are the pressures. And you have to think of pressure as a vertex-based quantity, a vertex-based scalar quantity. So Pj would be the pressure of the material that is being transported on the vertex j. And then we have edge-based quantities, which are the conductivities. And we call them Cij. So Cij would be the conductivity of the edge that connects the vertex I to the vertex j. Okay, and those quantities we want to describe in the modeling process. So we make a few assumptions, basic fluid dynamics assumptions. Actually, we assume that we have a low Reynolds number per cell flow, and then the per cell fluxes, Qij, again, fluxes are edge-based quantities. Okay, so Qij is the flux that you have on the vertex on the edge connecting the vertex I to the vertex j. And then Qij is just given by the product of the pressure drop, which is Pi minus Pj, and I divide by the length of the edge divided by Lij times the conductivity. Okay, that is basic per cell flow. And then I have one more very important ingredient, and that ingredient for the modeling is the Kirchhoff law. And the Kirchhoff law in mathematical terms is nothing but the conservation of mass law. And it basically says that if you take the sum of all fluxes, Qij, which enter through edges into one vertex, into the vertex I, okay, you sum those, scale them appropriately by the length, then that must equal the mass of the source term that you put in externally or take out externally from the network, Si. Okay, so here basically what you see is a conservation of mass law. Okay, and if you look at it in this form here, you already get the feeling of what it is, really. It's a discrete Poisson equation. Correct? Okay. Yeah, and then of course, I mean, the first question you ask yourself is this equation solvable? And then what you find is that a necessary condition for solvability is the global conservation of mass. So the sum of all externally added or subtracted mass has to be equal to 0. And that is not sufficient, I should say. Okay, you also need some connectivity of the graph assumption, but I'm not gonna go into this here. Okay, now optimal transportation means I have a cost functional to minimize. So you have to think of, when you have a biological transportation network, it costs something. Okay, and there is cost involved to run it. And that cost consists of two terms. The first term, that term that you see here, the Qij squared divided by Cij, is the so-called pumping power. So that is the cost that you pay to make the network operate, to make the network transport. And the second term, which is the Cij to the gamma term, is the cost that you pay even when there is no transportation. And that is called the metabolic cost. So what you have to think of the neural network in your brain. When you sleep, there is still a lot of function that is going on in your body, and you have to pay for that. And that would be sort of the metabolic cost. Okay. While the other term accounts for sort of actively pumping material through the network. Okay, so the pumping power, I should say, is set up by Joule's law, and Joule's law says that the power is equal to the potential difference. This is pi minus pi pj on the edge ij, multiplied by the current, which is qij. And that you can write as qij squared divided cij times lij, which is precisely the first term that you see in this cost function. Okay. And the second term, as I said, the metabolic cost, and you will see an exponent gamma here. So what we do is we basically assume that the metabolic cost is given by a power of the local conductivity. And that power is gamma. And when you go into the fluid dynamics, you can find that you will find that, for example, for blood flow, people use gamma equal 1/2. That's essentially Murray's law, the scaling law. While for leaf venation, any value between 1/2 and 1 is in use for the metabolic exponent. Okay, so you have a functional, you can write down the gradient flow. And what do I mean by the gradient flow? I mean here the L2 gradient flow of the cost functional E with respect to the conductivity vector C. Okay, and here the important thing to notice is that in this term you have the Qij's, and when you go back, you will realize that the Qij's are defined by Cij times the pressure difference, and then the pressure solves this equation here. So basically what you have in your gradient flow equations is you have a dynamic system for theCij's, but you have an algebraic side constraint. And the algebraic side constraint determines P, the pressure, in terms of C, the conductivity. Okay. So you have a system of ordinary differential equations for the edge-based conductivities, which has an algebraic side condition, which is a discrete Poisson equation. Okay. Now, that's the discrete modeling. It has many advantages. Yes.
The source term is always the same over time, or?
Well, that depends on the modeling. Let's assume it's constant. Yeah. But there is interesting modeling situations where you can vary it, actually, where it should be varied. Yeah.
Sorry, another question. So the evolution changes the conductivity in the network, but not the network itself.
Not the network itself. Very important point. And that is exactly what leads me to the mesoscopic modeling. Because, let me recap. So what you have here is you have transportation on a fixed graph. Okay. And that is, of course, not realistic, because what you really want to do is you want to model the evolution of the network. How does it come about? Right? So you need to change the graph within the process. Yeah? And well, that could also be achieved in a discrete modeling approach, but as I will show you, it's much more convenient and more intrinsic, I would say, to do it in a continuous approach. So let's go to mesoscopic. Now, the first thing that you do is, well, so far we didn't have any geometry in this. The graph was just an abstract graph. Okay, so you have to embed the graph. And let's assume that we embed the graph in the domain where the network lives. And let me call that domain omega. It's just a d-dimensional domain. Think of d equal 2 or 3. Okay. And so basically what we do is we embed the graph into the closure of C. Sorry, into the closure of omega. And then the next step is that we think of the local network conductivity as an independent variable. Okay, and we call it C. And what is C? C is a symmetric, non-negative definite tensor. Okay, and that funny space SD of R denotes the space of symmetric positive definite tensors, and the closure means that you also include those that have zero eigenvalues. Okay, and now the main idea is we formally reinterpret the pumping power, say, through the edge ij, and we make the pressure field, which was vertex-based, we make it continuous all over omega, make it live all over all the domain. And the basic way of doing this, write the pumping power again, so you have Qij squared divided by Cij, and then this takes this form here. Now, the Pi minus Pj can clearly be interpreted as a directional derivative once you have embedded the graph, right? So basically, what you can think of as an approximation for this is this term on the right-hand side here, where in the middle you see this tensor C. And from now on, I will treat that tensor C as an independent variable. So you have to think of as an analogy of kinetic theory here, right? So what we do here is precisely what happens in kinetic theory, say in the theory of the Boltzmann equation or of Vlasov transport equations, right? You go to phase space. Of course, in kinetic theory, you have a Lagrangian phase space, meaning the dimension of the phase space is 2D, two times the space dimension. This is not the case here, right? Because I have space, which is a d-dimensional variable, and I have the tensor C, which is a d times d plus 1 half-dimensional variable. Okay. All right. Now, the next thing that I do is I set up the joint probability measure of position conductivity of the network, and I call that measure mu. So what you have to think of is you have to think of mu of x and c, and now I'm being very imprecise here, but let me think of this as the joint probability of the network to have conductivity tensor C at the point X. Okay. And here this space P is simply the space of measures on that domain. Okay. Now, an important quantity, when you go to kinetic theory, right? What you realize is that people always talk about moments. Okay, and here it's exactly the same thing. So for example, when you compute the zeroth order moment of the measure mu with respect to conductivity, what you get is the network position density, which tells you where it is sort of very likely or unlikely to be within or outside the net. Okay. Yeah, here, this is just the notation for the projection, not important for the forest. Sorry. Right. Okay. So mesoscopic refers to scales. So what we talk about here basically is kinetic scales, which are in between the microscopic one, okay, which you can think of being represented by the discrete modeling that I've shown you, where you sort of model every node, every vertex, every edge, which here you don't. Okay, so you go to an intermediate scale, and then later on we'll also go to a macroscopic scale. Okay, so I mean, it's the same, it's exactly the same thinking that you have in kinetic theory, right? So I mean, in kinetic theory, I always talk about, in order to understand the scaling thing, I always talk about the space shuttle, right? So when the space shuttle is in outer space, right, you have a ballistic transport, then the space shuttle, which you can think of microscopic motion, right? When the space shuttle gets into the upper atmosphere, you are exactly in the mesoscopic scale, so you need a kinetic description for that. And when the space shuttle gets very close to Earth, the density of the air is sufficiently high that you can go to macroscopic, like Euler, Navier-Stokes, or something model. And here you have to think of it sort of in the same way. Okay, so now let me rewrite the cost functional. And here what I do is I want to make my life somewhat, maybe not simple, but bearable. So I take the Poisson equation and I regularize it. And you will see, mathematically, you will see in a moment why this is important, but it also has a physical meaning. And the physical meaning is that typically in any medium where a biological transportation network lives, you have something like a background permeability, okay, which is sort of not controlled by the network, but by the medium. It's just a property of the medium. And here the background permeability, I just call it R. Think of it as a positive scalar, can be X dependent, can even be a tensor, it doesn't really matter here. So I modify the Poisson equation by adding the permittivity of the medium, the background permittivity, and then I have this tensor P of mu. What's P of mu? P of mu, of course, has to be the permeability caused by the network, the permeability tensor caused by the network. And again, when you go to the modeling, what you see is that it has to be the first order moment tensor with respect to the conductivity of the measure mu. So that means you compute P of mu as the integral of C times mu. C integrated with respect to mu, integrated with respect to the conductivity. Okay, and that you plug in into the Poisson equation. And then, of course, all you need to do is take your cost functional and make it continuous as well. And the first term will be that quadratic form, which is just the gradient of P, where I write P of mu for the solution of the Poisson equation, okay? Multiplied by the conductivity tensor C, multiplied by P of mu, and then you have the obvious metabolic cost term. And then you have this correction term for the background permeability, right? So that is my continuous cost functional, okay, which describes the formation of the network. And think of it in the following way. This is a functional E that acts on probability densities, on the probability density mu. And again, the Poisson equation just comes in as an algebraic side constraint. Okay. So that's sort of the important message here. And again, in the permeability, in the Poisson equation, you have to compute the permeability tensor, which is the first order moment of mu with respect to the conductivity tensor. So there is a lot of sort of analogy to kinetic theory here. Okay, so the first thing that we have to ask ourselves is does the Poisson equation make sense? And here the important news is, well, it does make sense if the permeability tensor is L1. Okay, and that is important here, okay? If you have a measure mu, which gives you a permeability tensor, which is singular with respect to Lebesgue, you cannot proceed, okay? So somehow you have to, within a moment, you have to build this into the domain of definition of the function. Okay, so the theorem basically says, and this is very simple, this is standard, it says that if the permeability tensor is in L1, then the Poisson equation admits a unique solution, which is of course in H1, such that this quadratic form here is bounded, and then since you have Neumann boundary conditions, you can always shift by a constant, and I do that by choosing the mean value of V equals 0. Okay. So that's the solvability of the Poisson equation, which is trivial. Now, I need to choose a space for measure mu. Probability space itself is a bit too big. So what I do, because I need moments, I need at least the first order moment. But I can make my life a bit simpler by imposing even a second order moment with respect to C. And then I choose the probability, I base my functional on the space P2 of X, where X is just the scalar product of the closure of omega and the closure of the space of positive definite symmetric matrices. And I ask that the second order moment with respect to C is bounded. well, I don't need the first order moment with respect, I don't need the second order moment with respect to x, because here I assume I should have said that omega is a bounded domain in RT. Okay. Okay, now I need a topology on that space. And as a topology, well, you have a lot of choice here, free of your freedom, but what is sort of very promising is, of course, to choose the Wasserstein metric on that space. And just if you haven't seen it before, you probably won't make much of this anyway, but let me just say what it is. Basically, you define the W2 Wasserstein 2 distance of two measures, mu and nu, in that space P2 in the following way. You consider all the transport plans, which are called gamma. And what's a transport plan? A transport plan is essentially a measure on product space such that the first order moment of the measure, the moment of the measure with respect to the first variable is mu, the moment of the measure with respect to the second variable is nu. Okay, and then you integrate the distance function squared with respect to the transport plan, and then you minimize over all the transport plans. Okay, and that is the Wasserstein distance of two measures, and we call P2 equipped with that metric. We call it the 2 Wasserstein space. And what does the 2 mean actually? Well, it actually refers to the square here, and of course compensated by the square root outside. Okay, you could define the P Wasserstein distance by taking P here and 1 over P out there. Okay. And why is that a good metric? Well, simply it's a good metric because we know a lot about it. And if you want to learn about it, take Cédric Villani's first book, second book, the Ambrosio Savare-Gili book, and you will know probably, and you will read more about the Wasserstein distance than you probably ever want to know in your whole life. Okay, so let me get into some mathematical properties of the function. And what I want to show you here is that it's really a mean guy. Okay, it's not a friendly function. Okay, so again, here is the mesoscopic function LE. I set up the domain of definition as the set of all, as the space of all measures mu in the space P2, such that the first order moment, the permeability tensor, is in L1, and this gamma moment is finite. Okay, and that of course makes sense because I need the metabolic cost. Okay, now first thing you do, you compute the first variation. And when you of course compute the first variation, you have to be a bit careful because the Poisson equation comes in as an algebraic constraint. Okay, the Poisson equation is an equation for the pressure, and the pressure depends on the measure. Okay, so you have to be careful, but then you compute it and you find it consists of these two terms. Again, one term corresponds to pumping, the other to the metabolic cost. Okay. Here's the bad news. If you're in a non-trivial situation, meaning your external mass S is not constant 0, then you can immediately conclude that the function L has no critical point. Okay, and that is sort of bad news. It tells you, well, maybe you have chosen the space too big or something like that, right? So what we will do in the following, we will restrict the functional to certain submanifolds of the Wasserstein space. Okay, and of course we want to choose those submanifolds such that critical points do exist. Okay, well, now there is some news that looks good, at least at first glance. And the news is that E is a strictly convex functional in its domain. You would say, great, I can do variational theory on it, right? I have a convex functional, but the news is actually not so good because what you realize is, well, if you go to the previous literature on biological network formation, what you see is that you have convexity, typically if the metabolic exponent is larger or equal than 1. But here I don't make any distinction, okay? So what's going on? Well, if you want to do Wasserstein gradient flows, minimizing movement schemes and stuff like that, what you realize is that convexity as such doesn't really tell you all that much. What you need is geodesic convexity. Okay, and here what you see is that if you check only the metabolic cost functional, you realize, well, it's geodesically convex if and only if gamma is larger or equal than 1. So you get kicked back again, right? And the first term is actually, I mean, the bumping term, geodesic convexity of the bumping term is an open question. I think it's really a very difficult problem. Okay, well, okay, now you have sort of checked convexity, which is sort of bad news. Now you want to check lower semi-continuity, because this is really what you use when you do minimizing movement schemes, the Georgi method, right? In defining gradient flows. But here you can very simply convince yourself that lower semi-continuity in Wasserstein space is almost out of the question. I would say out of the question. Almost out of the question is not really a mathematical statement, is it? So you need to make the topology stronger. Okay, and for example, one way of doing it is taking measures mu, which are not only absolutely continuous with respect to Lebesgue, but have certain properties, certain LP properties. Okay, at least locally. Then, if you strengthen the space, if you strengthen the topology in this lower semi-continuity. Now, why does lower semi-continuity really fail in Wasserstein space? Well, you can check that very easily. If you choose any measure mu, which is such that the associated permeability tensor, P of mu, is orthogonal to Lebesgue, and of course the metabolic cost is bounded, then what you really find is that E of mu is plus infinity, because this is outside the domain of the functional as you have defined. Okay. Well, on the other hand, you can choose a sequence mu(n) of measures in P2, which are absolutely continuous with respect to Lebesgue, and which converge in Wasserstein to your measure mu. And for that sequence, you will get that the inferior limit of E of mu(n) is less than infinity. So that contradicts lower semi-continuity. So you see there is something going on. And actually, when you go deeper into this stuff, what you realize is that this behavior is really typical for functionals which do not grow superlinearly. Okay, and this is precisely what we are facing here. So you would think that growth is bad, but here growth is really good for you, right? Not only for coercivity, but also for reasons of lower semi-continuity. So here you don't have enough growth. That's really the point. Okay, now what do you do? If you go to variational theory, when you have a functional which is not lower semi-continuous, then you just make it lower semi-continuous by relaxing it. And the relaxation, E bar, usually is defined as the supremum over all functionals which are lower semi-continuous, say with respect to the narrow topology, and which stay below the original function. Okay. And the interesting thing is that what you can prove then is that the relaxed functional assumes really its minimum as the infimum of the original functional E, which actually turns out to be strictly positive. Okay. Okay, now, why was I doing all this? Well, what we are interested in is minima, critical points we don't have in general, but some kind of minima, at least on submanifolds. So we have to go to gradient flows, right? That's sort of the most intriguing way of getting to minima. Well, okay, here the thing is, I don't want to show you really the full Wasserstein gradient flow. I just want to make things simpler here. Let me start with restricting to a submanifold. And the restriction to a submanifold here is that I only consider monokinetic measures. And by monokinetic, I mean monokinetic in the conductivity tensor. So those are measures which are a product of a position density rho times a delta in C, which centers in some unknown tensor which depends on X. That's a classical monokinetic, right? And then when I evaluate the functional for the monokinetic, I get a functional for rho and C hat, right? And I can compute the Wasserstein gradient flow with respect to rho and the L2 gradient flow with respect to C hat, because that makes sense, right? And what you see is what you get is a system of two partial differential equations where the second one, the one for the conductivity, which is now a function of X, okay? C hat of X, right? Is a reaction diffusion equation with a non-local term here, which is the tensor product of gradient P with itself. And gradient P, of course, comes about by solving the Poisson equation again, right? And the first equation is a transport equation for rho, okay, with a pretty complicated transport field. But for this equation, you have a lot of hope, okay? For that, you can really work on. The next gradient flow that I want to show you is kind of a change of paradigm. So what I want to do is I want to, in some sense, I want to fix X. And I want to see the evolution occur through the conductivities. Okay, so what do I mean by that? What I mean is I take as a submanifold, I take the space or the manifold of all measures mu, which have a given zeroth order moment with respect to the C variable. So I prescribe the position density of the network rho. Okay, and I only admit measures which have that position density. And then, well, a priori, it's really unclear if this, what we call it a reduced flow, if this is a gradient flow, or if you can make a gradient flow of it. But actually, using pretty classical optimal transport techniques and working a bit on the metric, you can actually show it. It's a gradient flow, and you can write it down. And it's kind of only half ugly. So what you see here is the gradient flow for mu. And actually, I should say that this is, I'm a bit cheating on you here because it's not really an equation for mu. This is, you can think of it as an equation for the disintegration of a measure mu with respect to a given position density. It's a bit more complicated than that, but let's ignore that. So what you see, I mean, you get a transport equation. Okay, again, with this pretty ugly looking velocity field. But again, this is an equation that I would say has hope. Okay, now how can you interpret that? You can interpret it through characteristics. And what you see here is the XC characteristic system. And then along those trajectories, mu satisfies this kind of ordinary differential equation. It is not, but you can think of it in that way for a moment, right? And what you can read from this is essentially that mu decays along characteristics. If gamma is less than 1, it remains constant along characteristics if gamma is equal to 1, and it grows along characteristics if gamma is larger. Okay, so that's sort of basic mathematical properties that you can extract. And then, of course, if you know, for some reason, if you know the flow map of those characteristics, which is complicated because it depends on mu itself, right? It's again a nonlinear process. Then you can think of the measure mu at time t as the push forward of the initial measure mu0 along that flow map. That's a basic theorem from transport equation. Okay, now what does Wasserstein do? Wasserstein kind of emphasizes transport structure. It emphasizes diffusion and transport. You can say, well, okay, there is cases where reaction is more important than transport. Well, transport occurs through reaction. Okay, and then you can change the metric. And another kind of appropriate metric for all this is replacing the, I should put it this way, you replace the Wasserstein metric by something that is called the spherical Hellinger-Kakutani distance. That's a long name. It's also called the Fisher, in information science, it's called the Fisher-Rao metric. And the Fisher-Rao metric is the metric whose metric tensor is given by the Fisher information of information science. So you can think of it in that way. And I don't have time to go through all the details here, but basically, yeah, the nice thing about the spherical Hellinger-Kakutani distance is that for measures mu0, mu1, which are absolutely continuous to Lebesgue, you can explicitly compute the distance. Okay, and the distance is given by a very simple formula, which you see here. It's just twice the arcus cosine of the integral of square root of mu0 times square root of mu1. Okay, so you have a very good notion of the distance for absolutely continuous measures, of course. It's much more complicated if one of the two measures is not absolutely continuous with respect. Okay, you can write down, well, you can go into the gradient flow. Then what you need to do when you write the gradient flow is you have to set up the Onsager operator, and the Onsager operator, just this operator K here is just mu times the argument phi. And for the argument phi to get the gradient flow, what you have to do is you have to plug in the variation of the function with respect to mu. Okay, so that gives you explicitly the gradient structure and the flow, and what you see is the Fisher-Rao gradient flow then looks like this. And that is semi-ugly, I would say, right? Semi-hard to deal with. So you have this first reaction term, which comes from transportation. This is the reaction term which comes from the metabolic cost. And this is just the average that you have to take out in order to make sure that mu remains a measure during the evolution. Okay, this just fixes the mass. Okay, now stationary states. After you have absorbed all this, you need to ask yourself, what can you do about stationary states? And let me go again to the reduced Wasserstein gradient flow. So here you see the equation for the reduced Wasserstein gradient flow. Set mu t equals 0, compute equilibrium states, meaning what is under the divergence has to vanish, right? So what does that mean? That means a stationary state, which is a measure, okay, mu infinity, has to concentrate on the set in phase space, let me call it phase space, where this equation holds. Okay, now this equation for gamma not equal to 1, you can solve this equation. And what you find is that mu infinity, again, is a monokinetic measure. And it's nicer than that. The monokinetic measure concentrates on the tensor product of gradient P, tensor gradient P. And what does that mean? That means basically that if you put yourself on a position X, where the network position density concentrates, then if you think of the network as a system of tubes, then the tube that passes through that point is aligned with the gradient of the pressure. Okay, so that's a positive surprise once and for all. Right? Now, in all directions which are orthogonal to the gradient of the pressure, the network conductivities vanish and the material flow is entirely governed by the background permeability. Okay. Now, what you have to do is you have to take that monokinetic, compute the associated first order moment with respect to the conductivity tensor C and plug it into the Poisson equation and see what you get. And what you get is something cute. You get a P Laplace type equation. Okay. And for the P Laplace type equation, you have a lot of math tools that help you to solve it, right? So here's a theorem. The theorem says, if the external source term S is in L2, if your position density, network position density rho is in L infinity, if gamma, the metabolic coefficient, is larger than 1, then there exists a unique solution. Okay, of the Poisson equation. How do you prove that? Well, I mean, basically you have to go into Evans' book, right? And I apologize for this ugliness on the right-hand side. What you do is you set up the functional, which is, I mean, the energy functional that is associated to the P Laplace equation, which is of course such that the P Laplace equation appears as the zero of the first variation. And then you get a functional that looks like this, and this has all the good properties. You have uniform convexity, you have coercivity. Again, the Poisson equation is the Euler-Lagrange equation associated to that functional, and you get the result. Okay, so that's sort of good. Now you ask yourself, what happens for gamma equal 1? I said gamma larger than 1. Now gamma less than 1 is ugly, because you lose, okay, I should say this. Gamma less than 1 is a big problem because you lose convexity immediately. Okay. Gamma equal to 1 doesn't work either. You just cannot plug it in here, right? You have to do a workaround for gamma equal 1, and that is really nice. What you can do is, well, first of all, you realize that for gamma equal 1, the stationary measure is concentrated in that set. Okay? And that is completely different from what I've shown you before, because it restricts the size of the gradient of P. Because this equation tells you that the norm, the Euclidean norm of gradient P, tensor gradient P, has to be equal to 1. Okay, so you already smell the free boundary notion of the problem here. And actually, it turns out that what you get is a boundary problem in the specific form of the so-called gradient constraint variational problem. And what's the gradient constraint variational problem? Well, it's basically, you take this function, which looks like the Dirichlet integral. It is the Dirichlet integral, basically. But then you minimize over a set where you have a pointwise bound on the gradient of P. Okay. And that's, again, a problem that you can handle. I mean, existence is not a problem. Uniqueness, existence is not the problem. I think regularity of the free boundary is not really trivial, but never mind. Okay, semi-discrete model. Let me sort of at the end of this, let me reconnect to the discrete model that I've started with, right? So keep in mind, we have this mesoscopic measure mu. So what you might think of if mu is a measure that concentrates on a graph, something like that, right? You might get back to the discrete one, but there's a problem, right? If the measure concentrates on a graph, it has to be singular with respect to Lebesgue, then the moment will be singular with respect to Lebesgue, and you can solve the Poisson equation, right? So you have to do some kind of relaxation. And there is actually a pretty simple way of doing this. Okay, but first let me show you what I'm really talking about. So assume you have a network which is a fixed ground. Okay, and assume that your source term S concentrates on the graph. So concentrating on the graph means be it on the edges, be it on the vertices. We can take in both, right? And then I make this ansatz for the measure mu, which basically means that it's a Hausdorff-1 measure on the graph, okay? And, well, this is the first part, right? And the second part sort of describes the dependence of the measure with respect to the conductivity tensor. And then when you see Tij here, you have to think of the tangent vector to the edges of the graph. Okay, so here I basically assume that the conductivity is again aligned with the gradient of the pressure. Okay, now here is my relaxation of the functional, and if you sort of compare the two functionals one to one, you see that basically the only thing that I did to it is I did away with the condition that the gradient P has to be in L1, or in L2, sorry, gradient P in L2. Okay, so basically here what I do is I consider P as a function defined on the graph. And then when you compute the stationary, the critical points of that functional, what you find is you find a Poisson, actually a P-Laplace equation along the edges with some kind of transmission condition at the vertices. Okay, and when you assume that you do not charge the edges, but you only charge the vertices, then this model gives you precisely the discrete model that I've shown you in the very beginning. So it doesn't, I mean, the loop doesn't close completely because, as I said, you have to do one more relaxation to get here, but it sort of does something for you. Okay, at the end of this, I want to go to what we call the macroscopic model. So what do I mean by the macroscopic model? Well, again, I assume that my mesoscopic measure mu is a monokinetic in the conductivity tensor, but I assume that the position density is uniformly 1. Okay, so basically in the equation rho c hat that I've shown you, I'm doing away with the rho equation. Okay, so this is basically the thing that happens here. The functional then looks like this, and here I did something else to the functional. I introduced a regularization. I added the Dirichlet integral here, okay, for good measure, right? So I have 3 terms in this functional now. The first term is you can think of it as random motion in the medium. The second term is responsible for the transport, and the third term is the metabolic cost. Okay, and the L2 gradient flow is given by this system of equations, which we have studied, I think, very intensively. Again, I want to point out that this is coupled to the Poisson equation, right? Through the pumping term. Okay, and we have existence uniqueness result, at least for global weak solutions, if gamma is larger or equal than 1. Yeah, and for gamma less than 1, this is a question that I haven't even talked about it in the mesoscopic case. Basically, you can only expect local time existence because of the singularity in the metabolic term. Okay, so the solutions could actually die out in finite time. Okay, now I want to show you some, this is a numerical conference, right? So I need to show you some numerical results. And basically, what we did here is we tried to emulate the leaf the geometry of a leaf. And what you see here is 2D results where we vary the background permeability. So here in the upper picture, you see the background permeability is 10 to the minus 3. Here is 0. Here is 1/2 10 to the, here, no. Yeah, 1/2 times 10 to the minus 3. And what you see when you go into the details, when you kind of zoom in, is when the background permeability becomes smaller, you get more and more branches that show up in your network. But here what you see is really sort of, I mean, you embody all the difficulties of the model. You see that you have very fine structures and you have very huge gradient on those fine structures. Right? Okay. And here, again, no, sorry. Yeah, basically this is just a different way of representing the last plot here. Okay, the same picture. And here there's another one, there's another numerical experiment where we basically vary the metabolic constant, nu, and what you see is, well, I mean, On the top half of the picture, you see the energy to convince you that we are really at a steady state in what I show you here. And what we see here is as the metabolic coefficient becomes smaller, again, you see sort of more and more structure pop up in the network. But then again, you see also a broadening here in the stem. Yeah, and there is a various scaling laws that, of course, are going on in those results. Okay, so I think this is what I wanted to tell you. And yeah, thank you for your attention.
Very much for your talk, Peter. Do we have some questions from the audience, please? Could you please, Fabio, can you please pass the, sorry, thank you.
What happens when R is 0?
You tell me.
Because it comes as a regularizing factor.
Okay, well, okay. Okay, if R is 0, somehow in order to make sense of the Poisson equation, you need something else, right? So, I mean, we have some results for R equals 0 for the last model that I've shown when you start with, say, uniformly positive with the permeability tensor, which is uniformly positive, and then it will stay uniformly positive for some time, but you cannot expect. I think this is the most singular of all the limits that you have here. So that I do not know how to do away with.
Thank you.
Thanks.
Do we have any further questions? Oh.
So you presented results just for one liquid, yes? It could be actually two-phase, so many useful stuff could be transported, yes?
So, okay, so here, that's an important point. We didn't really go into the modeling of the material that is being transported, right? So you sort of have to see this as a kind of supermodel from which you have to develop your individual model. So for example, I mean, constitutive equations for blood flow are of course very different from neural from network of brain cells, right? Yeah. So in the end, if you want to apply this to a specific case of transportation, you need to put in more information on the material. You need to put in materials. For example, we had a collaboration with biologists on the leaf venation, and there we did exactly that. We modified the model such that you could sensibly speak of a leaf. Okay.
Thank you.
Yes, for example, yeah. But also, I mean, you see, this is sort of, I mean, what I've done here is basically based on fluid transport, right? So if you have ion transport, you need to add something to that, for example, right? And the fluid modeling, fluid dynamics will not do the job for you. But yeah, you have sort of many screws to turn here. Yeah. Yes, that's the way I see it. Yeah. Or of course, if you transport current, you need to add a Poisson, you need to add equations for electrostatic potentials and so on.
So I think if we, oh, Raul, please. Okay.
Thank you, Peter, for the nice talk. I have a very simple question about the beginning. You wrote the Kirchhoff law, right? And when you were examining the fluxes, you put the flux divided by L, the length.
Okay, now
you use that scale.
Okay, so here, okay, that's a very good question. Let me go back. Now, at this point, at that point, where I'm going to go back to, the L's really don't matter because I have an abstract graph. Why did I put them after all? because I just wanted to indicate orders of derivatives, right? So basically, what I wanted to say is this Qij contains a gradient of P. And then I want to say that this equation contains a second derivative of P, right? But here they are totally irrelevant at this point. They become important. I mean, the scaling becomes important when I embed the graph. Okay, here, abstract graph, the L's really don't matter. They were just added for, I would say, aesthetic reasons. Okay, yeah. And to indicate what comes next, yeah. So, I mean, the basic Kirchhoff law is this, right? Of course. And then, I mean, of course, if you know graph theory, then you see the graph Laplacian and so on. Yeah, of course. Yeah. But for me, a Laplace operator is always a second derivative, so I need some h square in the denominator. And I was raised as a numerical analyst.
I think that's all we have time for. Thank you so much, Peter, for the excellent talk. So that closes the 4 talks for today. Just to let you know that there is a welcome ceremony in Building 20 at 5 o'clock. That's with an introduction by former SEMSI Dean Omar Kaneo. Okay, thank you.